In 1687, Isaac Newton published the Principia Mathematica, establishing the mathematical framework for physical laws. To precisely describe the physical universe, physics relies on a strict mathematical language. If you have taken a high school physics class, you are likely taught a very specific definition of a vector, a physical quantity that possesses both magnitude and direction. That definition is incomplete. Take electrical current as a counterexample. Current clearly has magnitude, measured in amperes, and it has a strict direction, flowing along a specific path through a wire. But if you change the angle at which these wires intersect, the output does not change. A 2 amp and 3 amp current meeting at a 90-degree angle or a 45-degree angle will always output exactly 5 amps. They add algebraically, not geometrically. This reveals the strict third condition required for a physical quantity to be classified as a vector.
Having magnitude and direction is not enough. The quantity must explicitly obey the laws of vector algebra. In multidimensional space, orientation must mathematically influence the outcome. If the physical result ignores the geometric angle, you are dealing with a directed scalar, not a true vector. To build a true vector, we isolate its direction from its size, using a unit vector. By dividing a vector by its own magnitude, we strip away the scalar value, leaving behind pure directional DNA, denoted by a hat over the variable. This gives us the foundational orthogonal triad of space. We assign a specific unit vector to each axis, I hat for the x-axis, j hat for the y-axis, and k hat for the z-axis. These 3 unit vectors strictly form a right-handed triad. If you curl the fingers of your right hand from the x-axis to the y-axis, your thumb points precisely along the z-axis. Standard vectors, like velocity, point exactly where you are going. But when an object spins, its edges move in every direction at once, making a circular path difficult to track with a single linear arrow. To define rotation mathematically, we need a vector that stays constant throughout the entire spin. This is where we apply the right-hand rule to axial vectors, like torque and angular momentum. If the object spins in a plane, the only direction that remains unchanged is the axis passing through the center. By placing the vector strictly along this axis of rotation, we create a stable reference for the rotational force. These orthogonal unit vectors form an absolute grid. Every physical action, whether translating linearly across a room or spinning around an axis, is mapped mathematically onto this framework. The defining test that separates true vectors from scalars is geometric addition, governed by a perpendicular yields components b cosine theta and b sine theta. The Pythagorean theorem provides magnitude r, the square root of a squared plus b squared plus 2ab cosine theta. Vector subtraction follows the exact same logic. Subtracting a vector is simply adding a reversed vector, expressed mathematically as a plus negative b. By reversing vector b's direction, the angle between them becomes 180 degrees minus theta. Since the cosine of 180 minus theta is negative cosine theta, the algebraic equation updates, featuring a negative sign before the 2ab cosine theta term. The visual shift in geometry dictates an exact mathematical shift on paper. The algebra and the physical geometry are inextricably linked. Moving from a flat 2D plane into 3-dimensional space, we rely on vector resolution. Any vector can be perfectly shattered into distinct orthogonal components. A single 3D vector casts a perpendicular projection onto the x, y, and z axes. Mathematically, the full vector is the perfect sum of these parts. R equals the x component acting on I hat, the y component on j hat, and the z component on k hat. To define the vector's orientation, physicists use direction cosines L, M, and N. We measure 3 angles connecting the vector to each axis: alpha from the x-axis, beta from the y-axis, and gamma from the z-axis. Taking the cosine of each angle isolates the exact fractional magnitude operating exclusively along that specific axis. Squaring and adding these direction cosines locks into a single Pythagorean identity. Cosine squared alpha plus cosine squared beta plus cosine squared gamma perfectly equals 1. This identity guarantees these 3 orthogonal components capture exactly 100% of the vector's magnitude. No information is lost and no directional data overlaps. When it comes to multiplying 2 vectors, the geometry demands 2 distinct methods. Vectors interact differently based on whether they are maximizing their parallel influence or their orthogonal influence on one another. The dot product, or scalar product, strictly extracts parallel contribution. The equation is A dot B equals the magnitude of A times the magnitude of B times cosine theta. We see this in physics when calculating work, which is the dot product of force and displacement. By taking the cosine of the angle between them, we calculate only the force acting directly along the path of motion. The vectors multiply and collapse into a pure scalar magnitude of energy, stripped of direction. At the unit vector level, this means I hat dot I hat equals 1 because they are perfectly parallel. Dot I hat dot j hat equals 0. Orthogonal vectors share 0 parallel influence. Conversely, the cross product, or vector product, extracts strictly orthogonal contribution. The equation here uses sine theta multiplied by n hat, a brand new unit vector. The physical paradigm here is torque. Torque is the cross product of a radius vector and a force vector. By isolating the purely perpendicular force, the cross product generates a completely new vector pointing along the axis of rotation. Because of the right-hand rule, this operation is strictly non-commutative. A cross B equals negative B cross A. Reversing the order of multiplication reverses the resulting axis of rotation. The dot product reduces complexity into a pure magnitude of energy, while the cross product generates an axis defining the direction of a rotation. We can calculate this cross product without needing to graph it in 3D space by using a purely algebraic tool, the matrix determinant. By setting up the unit vectors in the top row and expanding the determinant, the mathematics automatically isolates the exact cross contributions from the orthogonal components. The study of vectors is a continuous translation between physical geometry and algebra. We construct geometric proofs for vector addition, shatter vectors into precise direction cosines, and define physical interactions through the dual rules of vector multiplication. This is exactly why defining a vector simply as magnitude and direction falls short. Vector algebra provides the essential mathematical grammar required to decode how physical forces actually govern our multidimensional universe.